Okay, so psi is the wave function. Psi squared is the probability density. It's the probability of finding an electron at a point in space. So it equals the probability divided by the unit volume. We're going to talk about the s orbital first. The s orbital is spherical, so that can be useful, s and spherical, right? The probability density decreases as we get away from the nucleus, and that makes sense. If we look at a plot of this, it resembles a multiple exposure photograph. It's important to understand the electron is not just moving randomly like a moth around a flame. In a sense, the electron's location is spread out over the entire volume of the orbital, because remember, it's a wave also, and waves can occupy lots of space, and yet if you touch the wave, like a wave on a string, you touch it, it freezes, right? And then it's not a wave anymore. That's kind of how electrons are. Okay, so this is a plot of the probability density. It would be like you've got a camera set up, and you open the shutter, and you get one dot. That's where the electron is right now. And then 2 seconds later, you do it again, and maybe it's over here. And so after a while, you get this dotted pattern, and we see that most of the time the electron's around in here, but then it is out here sometimes. I think of my son Andrew as being a lot like an electron. He's kind of unpredictable. And so if you were to take a picture of him where he is in the house at any given time, it could be unpredictable, right? When he was 2, he stole the neighbor's big wheel and drove it to my brother-in-law's house 3 blocks away. So normally a 2-year-old would expect it to be actually in the house or at least in the yard, right? But no, occasionally he's off somewhere else because he got out and nobody noticed. So that can happen with electrons too. So the probability density, psi squared, with the radius, we see that the probability drops off as you get farther and farther away. The problem with this is, though, would the electrons be at the nucleus? No, they shouldn't be at the nucleus. This implies that they are, because it's highest here. So this isn't quite right. So they fiddled around with that. Now we use the radial distribution function. The total probability of finding an electron within a thin spherical shell at a distance r from the nucleus. This gives us a better picture. So now we've got the probability divided by the unit volume times the volume of the shell at a distance r. So we multiply these two functions, and we get a better understanding of what's going on. So this is the resulting graph. Now there's 0 probability of the electron being at the nucleus. And the probability of finding the electron at this distance from the nucleus, as you move away from the nucleus, it goes up sharply. There's a maximum here, and then as you keep going out, it drops off. A plot like this tells us that the most probable distance for the electron in the 1s orbital of hydrogen is 52.9 picometers away from the nucleus. That does not mean that it is orbiting in a nice circle at 52.9 picometers. That would be so much easier to understand, but it's not that way. That is the same radius, though, that Bohr predicted from his model. That's not a coincidence. There's an important conceptual difference. The Bohr model has that electron orbiting. Quantum mechanics says the electron can be found at many distances, but 52.9 picometers is the most likely. The 2s and the 3s orbitals are also spherical. They're larger than the 1s, but they contain at least one node. So there's a cool simulation on your Mastering Chemistry that allows you to mess around with things like this. This is like a rope just being wiggled up and down, and it makes nodes. And those nodes are multiples of, or the distance from here to here is multiples of the distance between the nodes. It's a function. It's a point where the wave function goes through 0. And so what we see is here at the nucleus, the probability of finding an electrode is 0. And there's another place out here where the probability of finding the electron is 0. And if there are more nodes, those all represent places where the probability of finding that electron is 0.
What we have here is a frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. Sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just start to turn this on. Well, yeah, let's go higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that come down and reflect destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera. So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice, this is a node, and the middle is a node. So we have 3 nodes for this one. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5. And there we go. It's basically the scenario of a jump. Now, I can find any of the other, all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess, what is that? 25.5. And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1 and a half. 1 and 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with the high-speed camera and verify for yourself that it is 1 and 1/2 wavelengths. So again, third harmonic, 1.5 wavelengths. Well, let's go to the 6th harmonic. The 6th harmonic will just be double this frequency. So we go up to 50. And there we go. That's the 6th harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and the derivations.
Okay, so let's just look at this. Where is the wave in there? Obviously, I froze it so we can see the string is down here. But when this is going up and down, where is the string? It's kind of all of it, right? It's in all of it, and yet it's actually only in one place. This is the closest I can come to understanding this whole electron. How can the electron fill the entire volume of that sphere? Well, it's a wave function. And so in its wave function, it's filling that space. And you could do a probability of where you'd find this string. You'd probably find this string more frequently in the middle because it has to keep passing through the middle. Does that make any sense? Okay. Let's get back to PowerPoint. So that's what the node business is. The s orbitals at the higher principal levels have nodes in them. They're like the harmonics. And so for n equals 2, there's a node. And for n equals 3, there's a node. And if we look at the graphs, it's easier to see. There's this node here, so there's some probability here, and then it goes to 0. Then it goes back up. These are not this nice little sine wave of the string moving up and down, but you kind of get the same idea, right? And so for n equals 3, then we have 2 nodes. There's these 3 different sections. The n equals 3 s orbital is bigger in diameter, and it has more nodes. As you go up and up and up, they get larger and larger, and they each have an additional node. So each principal energy level has 1 s orbital. That's always the lowest energy orbital in a principal energy state. They're spherical, and the nodes, our number of nodes equals n minus 1. So this is where we kind of draw, make this into more of a hard shape. But the s orbital is not a blue rubber ball. It doesn't have, it's not a container for an electron. It's a region. It's easier to draw this way than with all the little dots.
So is that ball shape? Is that the atom? That would be like the graphical representation of the average?
This would probably, usually that represents the edge of 90% probability.
Okay.
Yeah. And, you know, I get hung up in details all the time. What's important here is that we get the big idea. If you're really into the details, you can go on and study physical chemistry later, and they'll give you more details than you ever wanted to know. The p orbitals. So in the p orbitals, L equals 1. And so looking at quantum numbers now, we've already identified that there would be 3 p orbitals in that p sublevel, and they have different orientations. So each of these orbitals has 2 lobes. It has a node at the nucleus, and so they're shaped kind of like 2 balloons or a dumbbell or something. Here's the multiple exposure view, and this is more of a solid surface view. So there's 1 p orbital that's aligned along the x-axis, 1 along the y-axis, and 1 along the z-axis. So there's 3 of them, and they're arranged perpendicularly to each other. So this is px, py, and pz. Each of them has a node at the nucleus. The probability goes up and then falls back down again. So that's what the L means. It's the orientation. D orbitals, there's 5 d orbitals in a given sublevel, the d sublevel. 4 of them are aligned in different planes, and then the 5th one is aligned with the z-axis, and that one's called dz squared. 4 of these are 4-lobed, and 1 is 2-lobed with a toroid. These guys are trippy. You like them? I'm sorry. So these kind of look like double p orbitals, don't they? But they're arranged in space differently. The p orbital would be along the x-axis. There'd be a p orbital on x, y, and z, and these are in between. So this one is in the yz plane. This one's in the xy plane, the xz plane, and the x squared, y squared plane, and then there's this guy. Yeah. He hasn't learned how to swim yet, so he's wearing a life preserver. I don't know. F. Okay, these get even crazier. Some weird sort of balloon art, right? I am not going to require you to know the shapes of those. I could not draw those off the top of my head. I'd be hard-pressed to copy them from the picture. As you go to these higher L quantum numbers, there are more orbitals and their shapes get kind of crazier, right? Okay, phase of an orbital. So remember, orbitals are mathematical wave functions. So it's like an equation that describes how that string is moving. That's what a wave function is. The wave function can have negative or positive values, just like the string. When the string is above the midline, you could say it's positive. When it's below the midline, it's negative. So the sign of the wave function is called its phase. The orbitals interact like waves interact with each other. If their wave functions are the same sign, they are in phase, then they are going to constructively interfere with each other. If they are out of phase, opposite sign, they will destructively interfere with each other. And this is really important concept that we're going to look at in another chapter when we talk about bonding. So phases. The s orbital can only have one phase. The p orbital can be up or it can be down. So this p orbital, one side is positive and one side is negative. And then when one of these interacts with another one, they can be interacting positively or negatively. So with all these weird balloon shapes, why do we think of atoms as spherical? Well, if you take all of these and put them all together, they are roughly a sphere. But an atom is not a marble. I like to envision them as marbles, but they are not marbles. They are these weird, complicated regions of probability wave function things. Any questions? That was just super clear, wasn't it? Not even.